In this video, we're going to examine conditionals a little more closely and talk about different ways that we can manipulate them. So in this section, we're going to create the converse, inverse, and contrapositive of a conditional statement. We're going to look at those three and talk about equivalences of different conditional statements. Then we're going to talk about only if statements, and then finally the biconditional or the if and only if statement. So first, let's talk about a generic conditional statement, if P, then Q. Remember, that's what this right arrow represents. If P, then Q. So we're going to talk about that sentence, that statement, talk about different things we can do with it. If we reverse the order, so if we instead say if Q, then P, then that is what's known as the converse of the statement. We represent that as Q implies P, Q arrow P. So that's going the opposite direction or opposite order. The inverse of the conditional statement is doing not both parts. So you're going not P implies not Q. So if not P, then not Q. And to be fair, the inverse is going to be the one that we look at the least out of these. The converse and contrapositive are going to be a lot more useful, but we'll talk about why that's true on the next page. The contrapositive is the weird one here. It is the converse of the inverse, or we are doing both the converse and the inverse at the same time. We're reversing the order and we're taking the not of both, the negation. So not Q implies not P. Note this is the inverse of the converse. So here, if not Q, then not P. So these are three different ways, converse, inverse, and the contrapositive, that we can manipulate this conditional statement and get some more use out of it. So let's look at an example. We have two statements, two simple statements. P, you are compassionate. Q, you contribute to charities. And let's look at our four conditional statements, the conditional, converse, inverse, and contrapositive. So to say P implies Q is saying if you are compassionate, then you contribute to charities. Q implies P. Again, this is the converse. We're going the other direction. That is, if you contribute to charities, then you are compassionate. Now let's look at the inverse. Not P implies not Q. If you are not compassionate, then you don't contribute to charities. And finally, let's look at the contrapositive. Not Q implies not P. If you don't contribute to charities, then you are not compassionate. So there are some equivalences within these four statements, and I urge you to pause the video and to try to think about what two statements are equivalent, or maybe more than two statements are equivalent out of these four statements. And we're going to verify what that's going to be on the next page. So given these four conditional statements, the conditional, the inverse, the converse, and the contrapositive, let's look at a truth table to see what kind of equivalences we have. Remember, we have two statements here, so we need 4 rows. And we look at it, we have 2 truths and 2 falses for P, and then we alternate the true false for Q. So let's do if P, then Q. Let's remember how we do this. If both parts are true, then the conditional will be true. If we have true and then false, then we get a false here. And then false for the antecedent, the P, will give us a vacuous truth. So there we have true, false, true, true. If we go the other way, Q implies P. The antecedent is now Q, the consequent is now P. So this should be that if the antecedent is true, the other one is true, then we get our true. If the antecedent is true and the consequent is false, we get false. And then we have our vacuous truth, the true, true. It might help to look at not P and not Q in this table as well in order to do the next two. So let's draw those in. Not P and not Q give us false, false, true, true, and false, true, false, true. Now we can think about the inverse and the contrapositive. So the inverse says not P implies not Q. The first two are vacuously true because the antecedent is false. The next one is false because it's a true and then false. And then true implies true is true. I'm going to label the trues a different color just so we can kind of differentiate them a little bit easier. There we go. And now let's look at the contrapositive. Not Q implies not P. Note that we have vacuous truth in the first and the third. We have a false in the second because we go from true to false. And then the last one is true because we're going from true to true. So although the colors don't matter, just kind of showing how we got those. The vacuous truths are yellow, the blue are where we have true then true, and the false is the false one. But if the colors don't really matter, we actually do have some equivalences. We can see that the first and the fourth row are equivalent. We have true, false, true, true. So this means that if you say P implies Q, that's the same thing as saying not Q implies not P. That a conditional and its contrapositive are the same, they're equivalent. So the conditional is equivalent to the contrapositive. We also have that the middle two are equal. So these are also equivalent. That means that Q implies P is the same thing as not P implies not Q. And really, this is the same idea. This is just the contrapositive of Q implies P. Right? Note this is, this is the contrapositive of Q implies P. So that means that the converse is equivalent to the inverse. So if we go back to the previous page, when we think about a real example to kind of get our hands in it, let's see if these equivalences make sense. So we said that that A and D should be equal because we have the conditional and it's contrapositive. So we said, if you are compassionate, then you contribute to charities, is equivalent to saying, if you don't contribute to charities, then you are not compassionate. And I urge you to kind of think about that in your head and try to make sense of it, right? We're kind of going backwards, but we know that it is necessary that in order to contribute to charities, we have to be compassionate. So if we kind of flip that around, that means if we don't contribute to charities, then we are not compassionate. And the same kind of thing is true for the converse and the inverse. Those are equivalent sayings. It's just a different way of writing it, and sometimes that can be very useful in logical arguments. All right, so we have our 4 conditional, converse, inverse, contrapositive. And now we found that the conditional and the contrapositive are equivalent, and the converse and the inverse are equivalent. So now let's think about only if. All right, we're going to look at this statement. A prisoner is paroled only if, that's our key word there, a prisoner obeys the rules. So we can write this as a compound statement. A prisoner is paroled is going to be our statement P. A prisoner obeys the law, the rules is going to be Q. So we have P only if Q. So let's see what this really means. This is what we're going to try to say is interpret this sentence. So here, P can only be true if Q is true. That's what P only if Q means. P can only be true if Q is true. In other words, if Q is false, then P must be false. That's kind of going the opposite direction. If P is only true if Q is true, then if Q is false, then P must be false. That is, not Q implies not P. And note that this is the contrapositive of P implies Q. And since the contrapositive and the conditional are equivalent, then we can say that P only if Q is equivalent to P implies Q. Now, maybe the biggest reason why we have to kind of bring this up is because when we write only if, the if part, or what comes after is after the word if, but really that's the consequent, and that can be a little bit confusing. So note that in this statement, this is the consequent, and this is the antecedent, even though the consequent comes immediately after the word if. But since it's attached to only if, then it really acts as a then, an if-then statement. So let's deal with another only if statement. Let's translate it to if-then, and we'll talk about some truth table with it. So the statement, a federal grant is given only if the artwork is not obscene. So first, determine the antecedent and the consequent of the statement. Well, the antecedent is what comes before the only if. So the antecedent is a federal grant is given. And the consequent comes after the only if. That is, the artwork is not obscene. So let's rewrite this statement with a more familiar if-then format. We say, if a federal grant is given, then the artwork is not obscene. So let's look at this truth table. Under what conditions is this statement true? Well, let's look at P and Q. Note that we could say that Q, or P, is a federal grant is given. And Q can be maybe the artwork is obscene. So we are looking at P implies not Q. So we have to deal with not Q first. So we'll do that. That's going to be false, true, false, true. And then P implies not Q. We have a false from the first because we have true, then false. We have a true for the second because they're both true. Then we have vacuous truths for the last. So we can say that this is only false if P is true and Q is true. P being true is a federal grant is given. Q being true is the artwork is obscene. All right. Lastly, let's look at the biconditional. And this is going to be the one that actually shows up maybe more than anything else other than just the conditional. So a biconditional, we're just going to give the really mathy form, the logical symbols, is P implies Q and Q implies P. That's how we read this statement. P implies Q and Q implies P. And we often denote that with a P with a double arrow, Q. And we read that double arrow as P if and only if Q. And this is sometimes abbreviated as PIFF, if and only if Q. So these three things are equivalent, saying P double arrow Q, P if and only if Q, P IFF Q, P if and only if. So what a biconditional statement is saying is that we're talking about the original conditional has to be true, and going backwards, the converse has to be true as well. P implies Q and Q implies P. Or we can write that as if P then Q and if Q then P. So let's look at an example, talk about the truth table for this. This is our general truth table for a biconditional. If a citizen is eligible to vote, we're going to call that our statement P. Then the citizen is at least 18 years old. So this is the statement P implies Q. Let's write the statement for the biconditional first. So P biconditional Q, if and only if Q, is going to be a citizen is eligible to vote if and only if the citizen is at least 18 years old. So let's talk about this if and only if before we kind of jump into the truth table. It's like we're doing two sentences at once. We're saying a citizen is eligible to vote if the citizen is at least 18 years old. So that's saying if the citizen is at least 18 years old, then a citizen is eligible to vote. And then we say a citizen is eligible to vote only if the citizen is at least 18 years old. And we learned on the previous page that that's the same thing as saying if a citizen is eligible to vote, then the citizen is at least 18 years old. So that is in that if and only if, that's both directions that we need. Let's look at the truth table. P implies Q is going to give us our true, false, true, true, the two vacuous truths at the bottom. Q implies P is going to give us true, true vacuously, false, true. And P, if and only if Q, remember, is P implies Q and Q implies P. So we need both of those to be true in order for this to work. And that's going to be true, false, false, true. And this is our truth table for if and only if statements. So it's only true if both P and Q are true or both P and Q are false. We use biconditionals a lot in mathematics and a lot past that as well. And this is really, we think about biconditionals are equalities. In mathematics. So if we can say that two things are equal, we are saying that there's a biconditional between those two things, right? Two, if and only if, 4 divided by 2, right? Those are the same expression. We're saying if it's 2, then we could do 4 divided by 2. If it's 4 divided by 2, we could do 2. And any equality you have in mathematics is really a biconditional.